Okay, for what we have in this part of chapter 5, we are looking at the least squares problem. And this, in a sense, we did look at back at the start of the course or near the start, and just kind of doing a little bit of revisiting. And let's say that for what we have in the case of this example, okay, we have in the case of the least squares regression line. And say that we have three ordered pairs, 1, 0, 2, 1, and 3, 3, and have those in R2. And it's asking, how can you find the line y is equal to c naught plus c sub 1 x that best fits these points? And one way is to note that if the 3 points were collinear, then the system of equations below would be consistent, okay, where we have c naught plus c sub 1 is equal to 0, c naught plus 2 times c sub 1 is equal to 1, and c naught plus 3 times c sub 1 is equal to 3. Okay, and so we have for the system, okay, we can write this in matrix form where we have the equation a times x is equal to b, where we have a to be the matrix coefficient, where we have from these three equations, from the c naught and the c sub 1 terms, we had the coefficients 1 and 1 from the first equation, 1 and 2 from the second equation, and 1, 3 from the last equation. And b consists of the constants, okay, that represent the y values, where we have 0, 1, and 3. And we have for the matrix x, okay, we have looking at the values of the coefficients, where we have c naught and c sub 1. And a sample of a least squares problem, okay, which we're going to be looking into. We have given an m by n matrix A and a vector B and Rm. The least squares problem is to find x and Rn such that ax minus b, okay, where we had the distance between ax and b squared, is going to be minimized. And the term least squares comes from the fact that minimizing the distance, okay, between ax and b is going to be equivalent to minimizing that distance's square, which is going to be the sum of squares. And okay, now looking at what we have for this portion, okay, we're looking at testing whether we have given points to be collinear, at least in the xy coordinate system. And we're looking at determining whether 1, 4, 3, 10, and -2, -5 are collinear. Okay, so if we go back to what we have with our equation, so you have y is equal to c naught plus c sub 1 x. And if I just switch to order where I can work with the numbers 1, 4, 3, 10, and -2, -5, and just taking the commutative property of equality. In other words, like going from a is equal to b is equal to a format. So we have c naught plus c sub 1 x is equal to y. And so we have regarding the ordered pair 1, 4. Okay, so we have 1 c naught plus 1x is equal to 4. And for 3, 10, we have c naught plus 3x is equal to 10. And with -2, -5, so you have like 1 c naught minus 2x is equal to -5. And setting things up in terms of the ax is equal to b format. So we have with the coefficient matrix A, okay, so we got 1 and 1, 1 and 3, 1 and -2. And again, x, we're looking at containing c naught and c sub 1. And for b, we have the y values 4, 10, and -5. And looking at what we have for the equation, okay, so we have a times x is equal to b. And so we have for this layout, okay, we got a 3 by 2 matrix multiplying a matrix that is 2 by 1, and the output is going to be a 3 by 1 matrix, which we have it with b at 4, 10, and -5 with the elements, and expressing what we have as an augmented matrix. Okay, so we have first row, we have 1, 1, and 4. Second row, we have 1, 3, and 10. Last row, we have 1, -2, and -5. And getting to what we have in converting to reduced row echelon form. So I'm going to take the first row elements away from the second row and also away from the third row. And we have in the rewrite, we have 1, 1, 4, 0, 2, 6, 0, -3, -9. And we have for the middle row to get this in terms of where we have the middle row, middle column value to be at 1. So I'm going to take half of the second row elements. So the second row becomes 0, 1, and 3. And then simultaneously, okay, taking the second row elements from the first and simultaneously adding 3 times the third row elements, or I should say 3 times the second row elements to the last row elements. Okay, we're going to have, for the first row, we have 1, 0, 1, followed by 0, 1, 3. And the last row we have it 0, 0, and 0. And we're going to have the system to be consistent. And as long as you have a consistent system, okay, the values in this case are going to be such that we have the points to be collinear. Okay, and so for what we have in this particular case with the 1, 0, 1, this will be referencing that C naught is equal to 1. And from the second row we had that C sub 1 is equal to 3. And going back, we have, again, for y, we have it's equal to C naught plus C sub 1x. Now it's going to be equal to 1 plus 3 times x. And you can always go back and check. Okay, so we have, see, like for y is equal to 1 plus 3x. Okay, so y is at 4. And 1 plus 3 times 1 is 4. And now for 10, 1 plus 3 times 3 is 10. And for negative 5, okay, you're going to have 1 plus 3 times negative 2, which would be 1 minus 6, and that will become negative 5. Okay, now looking at determining whether 1, 4, 3, 10, and negative 2, negative 7 are collinear. So I kept the first 2 points, but I changed the y value for the original third point. Okay, so we have in this system of equations, okay, this time the change up is with the last equation, we're going to have C naught minus 2x is equal to negative 7. So the coefficient matrix this time is going to be consisting of 1, 1 for the top row, 1, 3 for the middle row, 1, negative 2 for the last row, and which is the same as the prior example. Same thing for x, we have C naught and C sub 1, but for b, we got 4 once again, 10 once again, and instead of negative 5, we now have negative 7. And trying to see if these 3 points are collinear, so going back to ax is equal to b. And so setting things up, okay, so again, we have a 3 by 2 matrix and a 2 by 1. Product is going to be a 3 by 1. And expressing or translating in terms of an augmented matrix, so we have 1, 1, 4, 1, 3, 10, 1, negative 2, negative 7. And going through the process and converting into reduced row echelon form. Same procedures, okay, but this time if you notice, instead of having zeros across the bottom, okay, we have 0, 0, negative 2. And so for that particular reason, okay, we're going to have that system to end up becoming inconsistent. And so for what we have in effect, because the system is inconsistent, we no longer have the points to be collinear.